Okay, let's get started here. So this week we're looking at chapters 1, chapters 12 in the book. I'm going to do kind of a brief summary of chapter 1, and we'll go over some stuff with chapter 12, some math essentials. This is going to be a fairly math intensive class. Um, so with that being with your labs, make sure you have a calculator with you. Again, I'll say, if you're going to become a surveyor, get the NCES approved calculator on that list. Otherwise, for now, if you don't have one of those and don't want to worry about it yet, that's fine. Whatever calculator you have. So with chapter 1 in our construction and surveying layout book, a couple of things they talk about in chapter 1. And again, I'm just going to go over a summary. I'm not going to do the whole chapter itself here. Hopefully you will read it, the chapter. They start talking about planning. Planning is essential. Planning is crucial. Be ready for what the job is going to entail. You have a couple different jobs. You have an office crew coordinator probably at a job you're at, and you obviously have your field personnel. The office crew coordinator is going to be the one who has the contact with the client, which in this case will most likely be the contractor on the job site. They'll be the one in communication with them, find out what they're looking for, what they need. They should also pull together all the necessary plans and files that the field crews will need when they go out on site. As well as talking with the client, they'll work out a schedule of when they'll have the crews on site. Now, the field personnel, they have some other responsibilities. A lot of these responsibilities, too, will overlap a bit. The field personnel, when you're in the office, what you're going to need to do is have all your equipment ready. Make sure you got your trucks loaded. You got all your equipment, your ribbon, your lath, your hubs, your hammers, your tacks, mag nails, anything you would need out in the field. Also have all your equipment ready, your GNSS receivers, your robotic till stations, your data collectors, whatnot, and make sure you have your batteries charged. Once the crew coordinator gets all the files together, it's also the field guy's responsibility usually to upload all that data into their data collector as needed or necessary. So this chapter also mentions when you're out in the field, there are some successful characteristics or characteristics to be successful out in the field. Those are as follows: be committed, be willing to work, be responsible, be a questioner, be a learner, be a communicator, be a leader. I would personally put be a communicator at the top of the list. The field guys, when they get out into the field, they're not just going to jump out of the truck and start pounding hubs right away. You need to talk to the site super. You need to talk to whoever's requested the field work, see what they're looking for, see what they need, see how you need to stake out this information. We'll learn here when we start staking out buildings, utilities, things like that. We always stake the center of the structure or the corner of a structure, and then we provide offsets as well. Talk to the contractor, see what kind of offsets they're looking for. They can vary by project. They can vary depending on how deep they may need to dig. They need smaller, larger offsets. Communication is key. You want to talk to them. If you have any situation where, hey, we came across a situation where we need to push an offset out further, you need to let them know. As well as having that clearly marked on your stakes as you're staking things out. Put it in writing on the stake if you change an offset or something like that. But you definitely want to be willing. You got to be there on time. I think I heard in sports one time they said sometimes people's best ability is their availability. So you want to be there. You want to be available. They are depending on you to get work done. Being a questioner, question things. If you're unclear about a task, ask your crew chief, ask the site super, like, hey, we if there's a situation that arises, like, hey, we can't handle this the way you're asking, can we deal with this a different way? That's also a key part of the communication. But always ask for clarity. There is a fine line between, asking appropriate questions and asking way too many questions, and things that, you can probably figure out as you go along. Definitely be willing to learn. I always said this to my kids when they were younger. You don't have to know every single fact. You don't have to know every single detail. However, might need to you need to know where can you find the answer. Or even if you observe, watch how other people are working, you can learn how to handle a task, how to follow through, how to work through something. Quality control is very important when you're out in the field as well. I've said a million times, I'll keep saying it a million more. In surveying, redundancy builds confidence. Check, recheck, double check your rechecks. You want to verify that what you're putting in the ground, what you're staking out, is correct. We'll get into this more with some labs when we get out into the field. We'll lay out a building. We'll set the building corners and we'll pull offsets. We'll stake out offsets to the actual building corners themselves. A good practice to do, you lay this out with an instrument, change technologies. Grab a steel tape, pull between your offsets, check to make sure they're square, make sure everything looks good. It's always good to use another technology, pull some distances with the tape after you lay something out with your GNSS receiver or your total stations. Some office responsibilities include project documentation. That's also kind of an overlap. The office people are responsible for filing all of your data and maintaining the records. That's part of your part too. When you come back into the office from a day in the field, you download your data, prepare reports, maybe staked reports. That's something I'll show you when we get into some of the field exercises. When we do our staking, we'll come in, we'll download this, we'll provide an staked report that shows where we actually put stakes in the ground. Planning safety is another office responsibility. Hopefully they have a general idea of what you're going to come across and try to prepare for that the best that they can. It will not be perfect 100%. That is also something that is shared with the field people. Once you get on site, you might see something new. You need some different safety practices, different safety policies. But as far as like safety-wise goes, it is the employer's responsibility to provide personal protection equipment to the field crews. PPE is typically called. That would include things like hard hats, safety glasses, vests. A lot of companies, not all, but a lot of companies will provide like a stipend so you can go buy steel-toed boots. There could be potentially additional safety equipment that you need for job sites. Again, that's going to kind of fall on you when you get out to the job site and see, okay, here's something else we need to address. Preparing reports and record keeping is also crucial. Field books are a crucial record to document the work that was performed. That's something we will get into when we do the outside labs, is we'll keep field notes of what we did and how we did it. The thing with field notes is having a hard copy. You basically want to look and think, if something really went south on a project and maybe I got called into court, do I have enough documentation to prove what I did? Uh, Courts still look at hard copies of field notes and things like that, like that set precedence over digital files. So I know a lot of people, I was one of those people when I was young too, thinking, why do we need to write all these field notes down? We got everything collected in the data collector. Think to yourself, well, if you had to go to court and you had to prove this, knowing that the courts are going to put a lot more weight on your field notes, hopefully that will kind of change your thought process and mentality of keeping field notes. Some jobs too, depending on the size and the scope of the project, contractors might require daily reports. So they might require what tasks were completed, how much time it took to complete that. Some of it's part billing, some of it's just part documentation record keeping. Uh, Safety is a big issue out there too. Some companies and some projects will require the field crews to provide daily safety reports as well. Um, Safety is a big issue. It should be treated with a lot of respect and put a lot of weight on it, the importance of it. It's twofold. You know, they're telling you that they want you to go home safely every night, which obviously I think everybody would like to go home safely every night. And another thing is too, with providing the documentation and the personal protection equipment, they're also kind of covering their butts as well. I know it's something that's not really talked about much, and hopefully I don't get in too much trouble for saying it, but if something happens on the job site, there's an accident, and finds out you're not wearing your PPE or you were not following safety protocols, then that kind of falls back on you. So it's kind of also protecting the company. If there's an accident happens and you were following all your safety procedures, you're still injured. However, the liability kind of shifts off of you. Speaking about liability too, that's part of what makes a qualified land surveyor. So I think we all know, we've all talked in prior classes, I'll say it again, talking about that, is to become a registered surveyor, licensed surveyor, there is a specific amount of education. There is a specific amount of experience. Every state will require you to take 2 national exams that's provided by the NCEES. I could look up, but I don't want to right now, what NCEES stands for. National Council Engineering something or something something. National Council Examiners for Engineers and Surveyors. Thank you. Those 2 exams are between 6-7 hours long. The first one you take is the fundamentals of surveying. You can take that up to a year before you graduate college. After you get a certain amount of experience, you can take the professional practice exam. Also another between 6 and 7 hour long exam. Once you get those 2 exams under your belt, a lot of times you might have to get a little bit more experience before you can take a state specific. This also varies by state. After you pass the 2 national tests, get your experience, you can register and become a professional surveyor in the state of Kentucky. Excuse me, the Commonwealth of Kentucky. Every state varies, and there are multiple pathways to obtain your license. And that all has to come down with how much education you have. If you have a 2-year degree plus so many extra credit hours of surveying specific classes, and then quite a bit of experience. No path is the wrong way. However, I will say the shortest path, or the quickest path, would be obtaining your 4-year bachelor's degree, and you get the shortest amount of experience. Typically, it's around 4 years. Every state's requirements are a touch different. I can't speak for Indiana and Kentucky and Ohio. After you get your experience, you take your 2 national exams. You do have a state-specific exam you have to take. They're approximately 2.5 hours long. Once you complete those and pass, then you get your license for those states. Um, and with that, when you become a registered land surveyor, if you're working on your own, you need to carry insurance on there. It's and like an errors and omissions insurance. A lot of times you're working for bigger companies. Once you become licensed, they just add you to their company policy. But big mistakes on construction sites can cost lots of money, legally and everything else involved. Legally and whatever it takes to fix it. That kind of in a nutshell was chapter 1 of the book. Going on to some other things here. I wish this computer would not time out so gosh darn fast. There we go. Let's talk about some definitions and associated terms. In this week's module on Brightspace, I'm going to kind of add and populate some more information on here, as well as get this lecture posted online. I'd like to talk about some basic definitions. I do have a handout here to pass out for you. It is also or will be on Brightspace. Yeah, you're trying to make my life easier. That's something I should take advantage of. So talking about some definitions here, vertical line. It probably seems fairly self-explanatory. Vertical being straight up and down. Any point on the Earth's surface where a line follows the direction of gravity at that point. So at any given point, there is one vertical line only. This idea and this concept really gets pretty wild when we start talking about vertical and geodesy. It's a little bit different when we start talking about distances to ellipsoids and geoids and deflections of the vertical, but we won't get into that yet. Horizontal plane. At a point where a plane is perpendicular to the vertical line, there's only one horizontal plane through any given point. So we're familiar with horizontal. We're familiar with the horizon, how far out we can see. A horizontal line would be a point, is a point in any line that is perpendicular to the vertical line at that point. There's a lot of points and stuff. That sounds kind of confusing. At any point, there are unlimited number of horizontal lines. Easiest way just to visualize here, thinking of a horizontal plane, would be the floor, the ceiling. Looking at a vertical plane is a point in any plane that contains the vertical line at a point. There are unlimited number of vertical planes at any given point. So vertical plane, think of the walls in this room as a vertical plane. I'm looking at this kind of far away, and as I read it, it's like, oh, that kind of sounds funny. Maybe that's just me reading and not seeing that as clearly as I think I do. How about a level surface? This is a continuous surface that is at all points perpendicular to the direction of gravity. Now we deal with these quite often when we level up an instrument, level up our level when we're running level loops. A lot of levels in there. A horizontal distance between any two given points is the distance between those projected on a horizontal plane. Anybody have any questions on any of these so far as we're running through them? Clear as mud? Horizontal angle is the angle measured between two vertical planes. It is measured in the horizontal plane between two vertical planes, excuse me. So the horizontal line, we will actually be occupying a point, establishing a back sight, we'll establish a horizontal line. And when we measure the horizontal angular value to another point, another horizontal line, it's the angular value between two lines on a horizontal plane.
But that whole area is the horizontal plane?
Yes, on the horizontal plane, yeah.
Where you're, like, that angle, what you're turning from here to here is your horizontal angle?
Correct. Yes, well, we're turning from one line to another line, and the horizontal plane will be our horizontal angle. Same thing with the vertical angle. That's just turning an angle in the vertical plane. Now there is a little bit difference here, a vertical angle and a zenith angle. Your vertical angle typically starts with 0, looking at the horizon, and you're measuring up or down. That is your vertical. The zenith angle is also a vertical angle. However, we're looking at 0 as beginning straight up and coming down and going around. Zenith angle is a vertical angle that starts straight up and measures down. Your vertical angle starts at the horizon and measures up or measures down. Let's talk a little bit about mistakes versus errors. Mistakes happen from a lack of understanding plans, lack of knowledge of measurement techniques, and a lack of knowledge from equipment. Very simple. You say that's also like a human cause there. Blunders can be very large mistakes and due to carelessness. We definitely want to avoid blunders. That's why we check, recheck, double check or double checks. Oh, how can mistakes be eliminated? Chris gets ahead of himself. Check and recheck, redundancy, because redundancy builds confidence. Use 2 independent measurements, and that kind of goes to what I was saying before. When we get out in the labs, we'll lay out a building, for example. We'll set the corner of the building. We'll put some offsets at each corner. Take a tape measure. We know what our offset distances are. We can calculate what the diagonal distance between the offsets should be. We can take a tape measure, pull between our offsets just to verify that they're square and they're correct. Changing technologies would be a good way to say it. So if you lay something out with your GNSS receivers or your total stations, pull a tape measure out and pull some distances between to verify. Errors differ from mistakes. They always exist in every measurement. Typically, they're very small in size, and they're classified as natural, personal, and instrumental. 2 types of errors we have are systematic and random. The systematic errors conform to mathematical and physical laws. Magnitude and algebraic signs of the errors may be consistent or variable. Systematic errors can be eliminated by applying corrections. Systematic errors tend to accumulate, also called cumulative errors. Random errors remain after mistakes and systematic errors have been eliminated. These are caused by factors beyond our control of the observer, also called accidental errors. Random errors obey laws of probability. They tend to partially cancel themselves in a series of measurements, compensating errors. To kind of give you a little bit of a visual on that, probably talk about it again when we get out and do some angular measurements. And then maybe you guys remember from surveying fundamentals class when we did a closed loop traverse measuring the angles around a closed polygon. We doubled our angles where we took an angular measurement, flopped our scope, and then took that measurement again. To kind of exaggerate, if you're looking through your scope of your instrument and your vertical crosshairs is kind of exaggerating, leaning this way, when you flop your scope, they're going to be reading the other way. Take the average of those two, would cancel each other out. That would be a compensating error, just as a quick example. Any questions so far?
Is that what it's doing when it's like when you turn rounds?
Mm-hmm.
Is that what it's doing? Like on the total station?
Yes. So on a total station, when you're turning rounds, you're measuring your angle with the scope looking as a normal forward position. You flop the scope over and sight your back sight, foresight again. Yeah, that's trying to take care of the compensating errors. And again, yeah, just to kind of exaggerate to show you, like if your vertical crosshairs out, when you flop the scope, it's going to be the other way. So those two would cancel each other out. Accuracy versus precision. We always aim for accuracy. We always try to be precise. Accuracy denotes the absolute nearness of a measured quantity to their true value. So that is, say your target shooting, how close are you to the actual bullseye? Precision refers to the degree of refinement or consistency of a group of measurements. Multiple measurements with small discrepancies indicate high precision. Degree of precision is attainable and dependent on equipment sensitivity, observer skill, and I would even say redundant measurements. So again, if you're target shooting, you maybe put a nice pattern. You're not at the bullseye, but you're off to the side, but you got a real nice tight group of multiple shots. Those would be precise. There's a small discrepancy. Maybe not accurate, not close to the bullseye, but if you got a nice tight grouping in your shots, that would be considered precision. Does that make sense? Unit conversions. We'll look at some unit conversions. We'll do a lot of this math in the lab this week. We'll talk about feet and inches, feet, tenths, and hundredths. So surveyors measure in feet. However, we like to break down a foot into tenths and hundredths versus inches. It cracks me up thinking to myself, personally, as a kid in elementary school, I hated fractions in math. I don't know anybody, I've never met anybody who's like, I love fractions, they're the best. Never met anybody. Maybe one of you are. That's okay. So why in this day and age we use feet and inches and decimals or fractions of inches and things like that, it's beyond me. To me, it's just like still, it's difficult. Tenths and hundredths are fairly simple. Kind of think of metricizing the foot. We're going to break it down into tenths, and tenths of a foot, there's 10 tenths in a foot, and hundredths. So there's, oh no, get this thing turned and stop. Thank you. There's 100 hundredths in a foot. I like to think of this. I've explained this to contractors when they look at me and say, I don't know what this tenths and hundredths stuff is. I don't understand metric. It's not. It's like you understand a dollar bill, right? How many pennies are in a dollar bill? 100. It's a cent. It's a hundredth of a dollar. A dime, 10 cents. That's a tenth of a dollar. You know how to make change from a dollar? You should be able to understand this stuff. That's the way I kind of put it in my head. Yards and meters. Yards, there's 3 feet to a yard. Meter, there's 3 feet and change to a meter. I've never had actually have to measure or provide distances in yards. I take that back. One time, it was at a golf outing where we were doing a call your shot. We had an instrument set up on the tee box. People would pay so much money and say, I can hit it this far. And be sitting out in the golf cart out on the side of the fairway and come out and measure their shot, convert it to yards, and report back what they actually hit the ball versus what they called. I was sitting really far away and really far off the side, fairway one time behind some trees, and I had a ball bounce like 5 feet from the golf cart I was sitting in and thought, oh my God, who got a hold of this thing? It turned out to be, it was Bengals legend Anthony Munoz. Man, he really got a hold of that one. And when he came out there, I was like, man, I didn't think anybody would hit one this far. I thought I was safe. And he was like, well, you know, they told me I got extra if I could hit you. Thanks. That's one guy I don't want to get hit from. But other than that, like in real world situations, construction sites, I've never had to measure or provide any distances in yards. Meters, the same thing. There was a time in Ohio where we did try to convert to the metric system, and ODOT required you to provide all your measurements and all your distances and everything in meters. I believe that was done like in the 80s. So that was even before I started surveying. Yeah, they've since gotten away from that, and I mean, there's a slight chance you may come across an old set of plans, right-of-way plans or something from ODOT that are in metric, but chances are you're really not going to have to deal with that much, if at all. So when we talk about angles and direct measurements, horizontal, vertical, and zenith angles, we measure everything in degrees, minutes, seconds. That is a base 60, if you will. So there are 60 seconds in a minute. There are 60 minutes in 1 degree, 360 degrees in one full circle. I think everybody's kind of got that down, right? At least the 360. Again, I kind of think of like a clock. You know, how many seconds are in a minute? How many minutes are in an hour? Same thing. We also do deal with decimal degrees, and typically that's done in if you're doing any calculations out in the field. It's a lot easier when you're working between, you got a couple bearings, you need to know what the angle is in between. It's easy to convert those bearings to decimal degrees, do your adding, subtracting, whatever, convert it back to degrees, minutes, seconds. We will touch on this, go the longhand version. However, I'm a big fan of using the conversion on your calculators for it. There are gradients and radians, and maybe you guys remember that from trigonometry. It's where I think you start getting into like your pi over 2, there's 400 radians maybe in a full circle. I don't remember off the top of my head because I've never had to deal with them other than here in school and just talking about them. Has anybody had any experience with gradients or radians? Maybe accidentally getting your calculator stuck on gradients and can't get it back to degrees? That might be the only time I've ever had an instance where I've dealt with them. This sort of stuff here is kind of more of a, I want you to be aware of, I want you to know about it. We're really going to focus more on degrees, minutes, seconds, and decimal degrees. Because that's what you're really going to get into and really be dealing with on a daily basis. Okay, we'll talk about area, which is an indirect measurement. Area is distance times distance. We measure that in square feet, square yards, square meters, acres, and hectares. Correct me if I'm wrong, but I think the hectares or hectares or however you pronounce that is a metric unit, maybe?
Yeah.
Is it? That's kind of what I was thinking. Again, I have not had to deal with anything metric out in the real world. Square yards can be where when you start talking about material on a construction site. If you're talking about how much concrete, but that might actually be cubic yards. But I believe when they start talking about material and things like that, they start talking like how much area is that, how many square yards is that going to be? About the only thing I've ever dealt with in the real world has been square feet and acres. We will get into that in our lab. Anybody know off the top of their head how many square feet are in an acre? Anybody? Anybody? 43,560 square feet in 1 acre. How many acres are in a section? Anybody know that one? That isn't something we learned. 640? 640 acres in an acre, or 640 acres in a section in a square mile. One of the things we'll go back to, I think about this here now. We talk about feet, inches, tenths, and hundreds. Something else we'll also get into will be chains. I know we've talked about this in prior classes too. Surveyors historically measured in a Gunter's chain. We'll talk about that. We might even pull a chain out and do some measurements with that, just because we can. When you start getting into historical records and things to that nature, you'll see a lot of old plats, a lot of old deeds were written in chains. Knowing how to convert those to feet, decimal feet, is an important skill for a surveyor to know. And we also have volume, which is another indirect measurement. Distance times distance times distance. We deal with cubic feet, cubic yards, and cubic meters. Again, I've never had to deal with the metric portion. The only time you'll come across having to deal with volumes is if you're doing maybe a topographic survey on a stockpile. They need to know the amount of dirt on a stockpile, or they just dig a detention or retention basin before it fills. You want to make sure that they dug it properly and it will hold the correct volume of water. Okay, so here's some conversion factors. I think we may know the first two pretty easily. 1 meters, 39.37 inches in the U.S. survey foot. I'm going to bring this up real quick here, the U.S. survey foot. There is kind of at this time 2 feet in America. There's the U.S. survey foot and the international foot. I want to say it was December 31st, 1922, or 2022, the U.S. survey foot was actually officially retired and not used. We are to be using the international foot. Um, that's going to change here this year, most likely, where everybody's going to have to go to the international foot um, because of some geodesy type things. We're getting our datums modernized. However, a lot of things we still currently measure in today, at least in Ohio, Kentucky, Indiana, we use the U.S. survey foot. I believe Michigan, they actually have it legislated in that you're supposed to use the international foot. So checking laws and statutes of various states that you're going to be working in is important to know what you need to be using. One rod equals one pole equals one perch equals 16.5 feet. This also can be an important one to know because I have seen, like on some old plats from like the 1800s, roads and alleys be labeled in rods out their width. The almighty Gunter's chain, the surveyor's standard for many, many years. I was reading an article on Gunter. He was a mathematician and really had a thing about standards and standardizing things. But his chain is 66 feet long, comprised of 100 links. Each link is 67 hundredths of a foot, 0.66667, or however far you care to really carry that out. But when you divide the chain into 4, that's where the 16.5 feet this rod comes from. One mile is 5,280 feet, also equal to 80 Gunter's chains. And 1 kilometer is 1,000 meters. Again, when we get into labs and doing some actual math here, I want you to be familiar with the metric system to a degree, but I really want to focus more on Gunter's chains, feet, inches, things of that nature. Oh, here we go. Good. 400 gradients. I think I said radians. Gradients are a full circle. So 1 full circle, 360 degrees, 1 degree, 60 minutes, 1 minute, 60 seconds. Kind of like a clock. Except for where we say degrees, we're talking hours. But it's broke down at base 60, base 6. 400 gradients are a full circle, 360 degrees. 2 pi radians equals 360 degrees. Okay, some of you math folks who loved your trigonometry a lot still have that retained in your brain. And 57 degrees, 17 minutes, 44.8 seconds, 1 radian. 6,400 mils equals 360. Yeah, I'm going to focus more on this stuff here. We're not really, I want you to be aware of, but we're not really going to get into that much at all. Oh, 43,560 square feet equals 1 acre. I actually got that right, didn't I? Woohoo, Chris. Yay. Oh, yeah. I do have that slip that has all this broken down. I will have to make copies of that and hand that out. 10 square chains equals 1 acre. 1 square mile, 640 acres. 1 square yard, 9 square feet. Square meters, hectares, and square meters equaling an acre. And when we talk about some volume, going 1 cubic yard is equal to 27 cubic feet. 1 cubic meter is equal to 35.3 cubic feet. So when we talk about measurements, measuring is to determine an unknown value between two fixed points. How long is that property line? Well, we got to measure that. Layout, which is what we're going to be concerned with, is to determine a set point from a fixed point and known value. To be a little more specific with that, when we're doing layout, we will have two known points to establish a baseline. We know where they have known values. We will establish a baseline. We will lay out an unknown point, well, a known point with biangles and distances. Types of measurements we have here, we got distances, which we will pull tape measures. We'll use robotic total stations. You can use GNSS receivers. However, those are fixing positions and doing something we like to call coordinate geometry to determine the lengths. Angles, we use transits, theodolites, total stations. We used, in that fundamentals class, we used an old theodolite that measures some angles, or we might use the robotic total stations. I kind of was trying to get some more modern equipment in you guys' hands. My plan is for this class, with the lab portions, we will do the hand calculations as to what angles, distances, and things we need to lay our stuff out. Then once we get that completed, when we actually go out into the field and do the lab, we're going to use the data collector and robotic total station. So it's going to be a little geared a little bit more towards the field portion of the lab, like how you're really going to be doing it, more like you're going to be doing it in the real world. We can do some fairly simple calculations in the data collectors. We'll give you minimal information and show you how to figure out what you need to lay out from that. Measuring elevations, we use levels and total stations and GNSS receivers to some degree. When it comes to needing precise elevations or accurate elevations, the levels are going to be your best way to go. Total stations are good. The GNSS receivers are good, but it also kind of depends on the type of work you're doing. There have been times, for example, say laying out sanitary sewer. In this area, they might run that at a bare minimum percentage of slope, how much fall is in the pipe. When they're really critical on the elevations, I've seen pull out the level and grade using the level. If you got a lot of slope and there's not really a big issue with that, you can get away with using your total station. You're laying out rough grading or detention ponds, retention ponds, GNSS will work just fine as well. I have seen people, when they lay out curb for roadways, use a level to grade the roadways. I've seen people use total stations. I've used total station to do a lot of grading myself with roadways. Everything usually works out pretty good, as long as you check, double check, triple check. Check your checks. So when it comes to distance measurements, we have a slope distance, horizontal distance, and vertical distance. And the primary techniques we use for those, steel taping, or we still say chaining, and your total stations. When you're pulling a steel tape, you probably have a 100-foot steel tape. What you should have with you would be 2 plumb bobs, tension handle, hand level, I guess thermometer, and chaining pins. Maybe also from the fundamentals class, you recall trying to measure horizontal distances down the back hillside. You break and chain. That's very time consuming, very tedious, and there's a lot of errors involved in that. Although keep in mind, when the original surveyors were coming through here subdividing the land for settlers and settlement out west, uh, this is what they did. This is how they did it. Steel taping for horizontal distance, you need to have good horizontal alignment. And if you recall back to that horizontal lab break and chain, you have to have somebody keeping the head chainman on line. You need to have good vertical alignment because surveyors measure everything horizontally. So you need to make sure you have your horizontal steel tape nice and horizontal, and you're not doing any slope chaining. You have to have the proper tension pulling on it and the proper plumbing. Again, my plan for these labs will be, we'll use the steel tape to verify what we lay out, that we did lay it out correctly. We'll pull out that other technology. We're going to measure distances to verify that we put everything in the ground correctly. Using total station equipment, you need your tripod, tri-back, prism, prism pole. The thermometer and barometer, that's great, but you know what? I think we all have weather apps where we can pull that stuff out and look up the current temperature, current pressure in our phone. I do want to state for the record, when I first started surveying, I always had a total station and didn't have to pull distances like this. The EDMs, the total stations and things, have been around for a very long time, and the technology is trusted. But a key thing to know is that when you measure distances with a total station, that it is always shooting a slope distance, meaning as the ground lays. This requires it to also measure the vertical or zenith angle, and it actually calculates what the horizontal distance is that you're reading on the display. A lot of advantages over steel taping. You can go very far. This here says not as good for distances under 25 feet. I would still kind of argue that. I would say it is. And again, I'm just kind of going off of my experience out in the field. So again, the total station is actually shooting a slope distance and calculating the horizontal distance. It's shooting a slope distance is either reading a zenith or a vertical angle, as we talked about before. Calculating that, your slope distance times the cosine of your vertical angle is your horizontal, or your slope distance times the sine of your zenith angle. Any questions on that? Zenith angle is equal to 90 degrees minus the vertical angle. Horizontal angle measurements, vertical angle measurements, direction. We're going to talk about bearings and azimuths. This is very important to the surveying world. We're going to take bearings, convert them to azimuths. We're going to take azimuths, convert those to bearings. We're going to learn how to calculate the angles between azimuths and bearings. We will also even learn how to break these down into their north-south component and east-west component. You understand what I mean there? I'm just going to draw for the fun of it because I can. You have a line going in the northwest direction. You have some bearing listed. We'll just make up something here. 35 degrees, 26 minutes, 47 seconds west. What we're going to learn from this is how to break down that line into an east-west component, north-south component. This would be your north-south component, your east-west component. So turning it into a right triangle. Right triangles math is going to be crucial and really the basis of everything we do surveying calculation-wise. Any questions? Not yet? Still awake? Barely? Angle measurement equipment. The direct measurement would be with your total station. And meaning direct measurement is where you're sitting basically on the vertex of a point of that angle. So say for example, you set your instrument up at this point. You're going to back sight this point and establish a baseline. You have some other point over here. You turn and sight. This is your direct measurement. You're going to actually start here, measure this value in between the lines. That is a direct measurement of an angle. Does that make sense? Indirect measurements used with steel tape. So that would be things where you have a distance here. Maybe you have a distance over here. It is possible with 3 distances of a triangle to start calculating the interior angles. But when you're measuring distances and calculating anything, that's going to be your indirect method. Just for the fun of it, one time, back when I first started surveying, we had to calculate every angle and distance we turned out when we were laying stuff out. And there were times where there was a couple times where we actually had the distance of 3, distance all 3 sides of a triangle, and we needed to calculate the angles for whatever reason. I wrote a little program for my calculator just for the fun of it because I wanted to actually run through the program and start calculating all the angles for me. I don't know. I thought it was fun at the time. So with angle measurements, we measured the interior angles of a closed polygon. Angles turn left or right. 99.999% of the time, you are always going to be turning angles to the right. And when you're looking at a closed polygon, the theoretical summation of all the angles, n minus 2 times 180. I think we probably remember this from a prior class. n being the number of sides or the number of interior angles, minus 2 times 180 degrees, will equal the theoretical sum of all the interior angles of that polygon. An interior angle and an exterior angle equals 360 degrees. So let's start all over here. You have two lines. The angular value between those two lines is going to be your interior. We'll just call that I. If you were to measure around the outside, we're going to call that angle the exterior. The sum of your interior and exterior will equal 360 degrees. Deflection angles. We will get into calculating deflection angles, particularly calculating our way through a horizontal curve, like on a roadway alignment, for example. But what that means here, at least from this standpoint here, is measured from the prolongation of the backside. So if you did have a line from, you got your 2 points, you're going to go this direction. You got your instrument set up here. You're taking your backside over here. Prolongate, you extend your backside, and your deflection angle is actually going to be like so. Deflection angles can be to the left or to the right. I think I've seen once or twice some deeds that actually gave the directions around the parcel as deflection angles. It's kind of weird. You don't run into that very often. But we will come across this and calculate deflection angles later on in the lab. Again, our vertical angles we're looking at, they begin at the horizon. So say, for example, you set your reference backside 0 degrees is going to be on the horizon and measuring up or down. Typically, when you start the horizon and start going up, it's going to be a positive, looked at as a positive angle. When you start at your horizon and go down, those vertical angles are looked at as a negative. So your zenith angles, again, I mentioned before, they start from the zenith straight up and they go all the way around. 180 degrees will be looking straight down, the nadir. 90 degrees and spin around to 270 degrees, you're at your horizon. Now, one thing I kind of look at this and think about is when we start talking about bearings and azimuths, bearings never go greater than 90 degrees. They come off of the north-south line. I kind of think of like vertical angles in that instance here. Azimuths start due north on a horizontal plane, wherever due north is, and go all the way around, kind of like your zenith angle in a vertical plane. Does that add more mud to the water? Does that make sense? So when we talk about horizontal angles and measurements, we're talking about direction. I always seem to kind of jump a touch ahead of myself here. One of the major methods of labeling direction that you will see on plans, on survey plats, read in deeds, will be referencing bearings. Okay. So they come off of the north-south meridian. I don't know if I like saying meridians, two reference meridians. Just kind of the north-south line, your one meridian, north-south. They are turned clockwise or counterclockwise, never greater than 90 degrees. So they fall into four quadrants: your northeast quadrant, southeast quadrant, southwest quadrant, northwest quadrant. They always start at north and go either to the east or to the west, or they start at the south meridian and go to the east or go to the west. Never greater than 90. Does that make sense? Your azimuths, okay, there's one reference meridian, so north. Says they can be turned clockwise or counterclockwise. I've always seen them going clockwise. So starting due north, heading towards the east, going all the way around back up to north again, a full circle. So when you hit due east, a due east azimuth would be 90 degrees. Due south would be 180 degrees. Due west would be 270 degrees. And then back up again. Make sense? Maybe? Yeah? So some of the things we'll look at this week in our lab time will be some direction problems. We'll convert bearings to azimuths, convert azimuths to bearings. We'll determine the angle between two directions, so they could be azimuths and or bearings. We'll determine the direction of another line. So if we know the direction of one line and the horizontal angle between two lines, we can calculate the direction from that. This is all just kind of the textbook theory type stuff here. We'll actually get into doing the math in the lab time this week. I think everybody's okay with not going outside this week. It's supposed to be like in the 20s. However, like I said earlier, this class, we'll do our lab up in room 132. And I'll say dress appropriately, because that room, I think, will get all the way up to a nice balmy 58 degrees. So might want to wear a jacket and or stocking hat for lab, even though we'll be inside. Elevation is, the vertical distance. Three primary types of leveling: steel taping, differential leveling, and trigonometric leveling. I would say for the steel taping, that would basically be like putting a tape measure from the floor to the ceiling to measure how tall the wall is. Pretty simple, pretty basic. Differential leveling will be where we set up a level in some random place, establish a horizontal plane, read a vertical difference off of a benchmark or a known elevation, turn to another probably known point of an unknown elevation, read a vertical difference there, and calculate what the elevation is. So we're going to transfer elevations that way. A little bit of math involved with the differential leveling. It's just adding and subtracting, nothing too crazy, nothing too difficult. Trigonometric leveling, again, is kind of what your total station's doing here. This requires some more math. This is where you need to know your slope distance and either your vertical or zenith angle, as well as the heights of your targets that you're shooting. Touch more math, still nothing too terribly complicated. So steel taping, like I said, reading direct vertical distance, that'd be like putting a tape measure up against the wall and just measuring your straight distance. Your differential leveling, like I was just kind of talking about, you're reading direct elevation difference from a known horizontal plane off of a known benchmark elevation and transferring that elevation to another place. Some differential leveling techniques are running what we call level loops. What that will incur is we'll start at a known elevation, run transfer elevations around known points of unknown elevation, and tie back into that benchmark for our closure to verify that we ran everything correctly. Profile leveling is where we say take some side shots. So it's doing your regular differential leveling with level loops, but instead of kind of traversing from between points, you'll take some side shots as well. Those are kind of free floating. There's really no checks to those. Differential leveling this, I'm gonna kind of just flow through this. But, start off with your elevation. What the station is, what your backside rod reading is, calculate your HI, turn, push foresight, subtract that from your HI, and come up with your next elevation. Personally, when I make my notes, I always put a little plus sign in the backside column, and a little minus sign, just so I remember. Add your backside, subtract your foresights. Yeah. This leveling, again, you're gonna be doing with the total station, shooting your slope distance, measuring your zenith or vertical angle, and doing some math there. You need to know the heights of your targets as well. Fortunately, when we set up a total station, we can plug in the instrument height of our point. We know the height of our prism pole, and when we shoot, it's going to calculate all of that for us. Nice and handy. With the trigonometric leveling, not as good as differential. It yields quick results, especially for large elevation changes. Again, it would really kind of depend on what kind of project you're working on. If you need to run an actual level loop, or if you can get away with shooting elevations with your instruments. Your vertical distance is equal to the slope distance times the cosine of your zenith angle. So your elevation is going to be elevation A plus your HI plus your vertical distance minus your HR. Horizontal radius. Question? Okay, something here I just want to show you guys real quick is see if I can transfer this real quick. This is straight out of our construction book. Talking about plane geometry, various angles, you guys all remember geometry from high school probably still. Right angles, acute angles, obtuse angles, complementary angles, supplementary angles. Different parts of a circle, the circumference, diameter, central angle, radius, what a tangent line is to a curve. This is literally copied straight out of the book. So hopefully you have your book. This is in 12.4. Talking about polygons here, a triangle is a three-sided polygon. A quadrilateral is a four-sided polygon. Can include parallelograms, rectangles, squares, trapezoids, so on and so forth. We'll remember some of this too from fundamentals, where we talked about the sum of the interior angles of any polygon, n minus 2 times 180. N being the number of sides of your polygon or the number of interior angles. The sum of the exterior angles of a polygon is 360 degrees. Pretty wild. Right triangle trigonometry right here. Your Pythagorean theorem is key, critical, crucial to know. Keep that locked into your memory. C squared equals A squared plus B squared. C being the hypotenuse, which is the longest side. Um, 3, 4, 5 triangle is very important in construction. Your A lot of times you're measuring out things that are square. Building interior angles, building corners are 90 degrees. This is a nice little ratio here, 3, 4, 5. If, say, for example, you measure up 3 feet, 3 meters, 3 yards, whatever, 3 feet, you measure out 4 feet, the hypotenuse between those will be 5 feet exactly. This is unitless because it is a ratio, so you can expand that to whatever you want to be in order to create a nice right triangle. This is your friend. Learn this, love this. In surveying, pretty much all of the math, 90% of the math you will ever do has to deal with a right triangle. The trick is, sometimes we like to start calling sides different things, give them different names, but it's all still the exact same math. So in this case here, when you look at where the interior angle is, where you may have a number, a value, the side adjacent to that angle is going to be the adjacent side of the triangle. The side opposite of that angle is your opposite. And again, your hypotenuse is the longest side. This right here is critical. Sine of that angle is going to be equal to the opposite side divided by the hypotenuse. Cosine of that angle is the adjacent side divided by the hypotenuse. The tangent is equal to the opposite over the adjacent. This is crucial. Now, some things we will get into here would be oblique, non-90 degree triangles. What we have is the law of sines and the law of cosines. Depending on what kind of values you have, you can calculate pretty much every other part of the triangle. The law of sines states, as we're going to look at this triangle, let's look at this triangle here real quick. So we're going to call it each side lowercase a, b, and c. The corresponding angle across from those sides will be capital A, capital B, capital C. Lowercase a is this side, angle A is across from it. Side C, the angle is across, angle C is across from it. So with that, the law of sines is equal to side A over the sine of angle A is equal to side B over the sine of angle B. Side C is over the sine of angle C. So it's kind of a cross multiplication thing here. It depends on what information you have. You can kind of plug and chug and remove. If I have side A and angle A and maybe angle C, I can take out the B portion and put in my information that I do have and solve for the corresponding information that I need. The law of cosines is a touch longer. C squared equals a squared plus b squared minus 2ab times the cosine of angle C. So the c squared, a squared, b squared here, these are the lengths. These are the sides of the triangle. This is the formula that you can manipulate. If you have 3 sides of the triangle, you can calculate an interior angle. Once you have that, you plug it into the law of sines, calculate your other interior angles. Another thing we're gonna get into here, talking about is coordinate geometry. This gets into when we start having coordinates, a northing and an easting. Or if you think of like elementary school math or high school math, and a graph paper, you had X and Y values for a point. Well, great, now in surveying, we're gonna take the X and Y and we're gonna flop them. Your Y is your north and your X is your east. Let's not make it any more confusing. So if you have coordinates on two ends of points, you can calculate the direction and the distance. I mentioned earlier, we're gonna kind of break this down too. If we have a bearing and a distance, we're gonna break that down into the XY component, or northern and eastern components. That's gonna be this here. The distance is really just a squared plus b squared minus c squared. So you take the difference in your northings, which would be this vertical component, north-south component. Take that, square that difference. Difference in your eastings, which is going to be the east-west component. Take that difference to find the side of the triangle. Square that component. And together, take the square root, there's your distance. Wow. Amazing. I know.
Yippee.
I see all the light bulbs trying to click on.
Woo.
The direction, you take your difference in your eastings, divide by the difference in your northings. That will give you the arctangent, atangent, whatever you want to call it, of that angle.
Could you use that to determine magnitude?
I guess you could call direction magnitude, same difference, kind of which way it's going.
Okay, that
Yeah.
actually might be really useful. I'm in
Very useful.
the structural systems class, and that is a lot more math.
Well, you're probably still looking at vectors,
Right.
breaking down the XY components.
Right, that's why I was recognizing
Yeah,
it, yeah.
I mean, it is a vector. I think the magnitude would be the length,
Right.
not the direction.
Okay, I misspoke.
Yeah, I was thinking it'd be useful to help find the angles, because that was the thing that was tripping me up. We have to add magnitudes to get what direction and in what strength.
Huh. I don't know anything about it.
Okay. See, this is why you want to not become an architect, you want to become a surveyor.
Yeah. I'm taking this class, so
I
I can
know.
maybe do construction layout.
Adrian, I'm so happy to have you here in class.
I'm happy to be here in class.
Adrian, can I see one of those problems under class?
Yeah. I have a whole blank packet if you need.
I think I know what you're, I know what you're talking about.
So here's all the various formulas and relationships related to a 90-degree triangle. Again, if it's in the book, please look at this, read it, study it, learn it, live it, love it. And the same thing here for oblique triangles. Alright folks, so for lab this week, we're gonna sit in a little bit of a cooler room than this, and we're gonna do math, so please make sure you have your calculators with you.
I need to charge mine.
Chart, make sure your calculator is charged. That's really about all I have for today. Let's see, one more page. A couple more pages. Just wanna show you that's available here in the book. I might actually just throw these copies up on Brightspace so you have them as well. Various area computations, good to know. And various volume computations.
everything you want to know, but we're afraid to ask. So I'm gonna leave you with one little bit of advice. If you all are cold this time of year in your classroom, go stand in the corner, it's always 90 degrees. Thank you, good night.